I think that probably you should be able to listen to us. I am Nazareno Pierdicca. I am from Sapienza University of Rome, and currently I'm chairing the Modeling in Remote Sensing Technical Committee of the Geoscience and Remote Sensing IEEE Society. And there is only also a chat message. Okay. If there are problems with the audio, please add a message in the chat. But I hope that now it is working. And I would like to thank a lot Professor Kun-Shan Chen, who probably you know is very expert about modeling of scattering from rough surfaces. He's from the Institute of Space Earth Science in Nanjing University, Suzhou in China. And he was so kind to accept to give this webinar. As usual, the direction of the presentation will be around 40 minutes, about 40 minutes. And then we will have some time for question and answer about the webinar and the topic of the webinar. I think that this is all from my side, and I would like to give the floor to Professor Kun-Shan Chen. So, Kun-Shan, I think you can start when you want.
Okay, thank you for the introduction. I will turn on my video. So, dear co-worker and maybe struggle of the modeler, good morning, and maybe good evening for other people. So pretty much I'm very honored and humbled to give this short talk on the modeling of microwave scattering and emission from rough surface. Thanks to Professor Pierdicca for inviting me to come to this talk. I would like to also thank GISS and the MIRS for providing the opportunity to bring together the model users. So in this talk, I'm not going to report how much the progress has been made on the modeling, nor about which model is performing best, but instead I will share some experience on the use of the model. So here is the So here is my agenda for this talk. I will give a very brief introduction and background. And I also want to point on the rough surface model itself, followed by physics-based modeling, including the scattering and the emission, particularly from the rough boundary. And I will select some illustration and the data interpretation, how to use the model for the purpose of microwave remote sensing. And finally, I'll give some remark and maybe provide some future work. So microwave remote sensing is well known to provide deeper penetration into the medium. And the microwave cell is very sensitive to the roughness and the dielectric property of the rough boundary. So in terms of rough surface scattering emission, the scattering itself is all about the interaction of microwave with the rough surface related to the diffuse and or specular reflections. And the talking about the emission is all about the natural thermal radiation from a rough surface, which is multiplied by the presence of the roughness effect. So in natural scenes under the sensing, there always exists rough boundary, such as the sea ice over the ocean. So the surface scattering emission or the effective reflectivity model is one of the essential components in many applications of microwave remote sensing of a geophysical property in the complex Earth terrain. So the purpose of the model essentially provide us descriptive and or predictive measurement by the microwave sensor and a set of sensor parameter for a sensing scene, which the rough boundary of encounter. So the scanning model help predict how much the microwave are deflected or redirected when it encounter the rough surface, which is maybe included vegetation canopy or other materials. So the model are key to understanding the surface roughness effect and the soil moisture and the land cover, etc. As for the emission model, we focus on how the surface emit microwave based on their temperature or emissivity. So basically, they are used to retrieve the temperature profile, moisture content, and then maybe other geophysical parameters from the emitted microwave radiations. So both the scanning model and the emission model are essential for accurate remote sensing, which is enabling extension application like weather monitoring, climate study, and the environmental mapping. So some of the key applications include the ocean salinity, ocean wind, wave high, oil spill detections, etc. As for land, soil moisture maybe is one of the most important geophysical parameter to be inverted. As for cryosphere, we are essentially interested in mapping the snow, ice, the freeze zone detection. So the rough surface actually, like the ocean wave, is one typical random rough surface. The ocean wave itself is very complex due to the wave motion, breaking wave system form, etc. So like the complexity of the microwave and the ocean wave interactions is very complicated due to the orientation, motion, Doppler spreading, hydrodynamic modulation, among other factors. So in terms of emission, the rough boundary effect has a three aspects. So from plane boundary, there's upward emission up from the lower media up to the air. But when there's a rough boundary present, three effects are apparent. The first is the propagation angle from the up to air is changed. And also the effective direct constant is changed due to the presence of the rough boundary. And because of that, the more interaction between the boundary and the layer are created. So from emission point of view, the rough boundary can be viewed as a layer. So on the average, it creates a layer of thickness. So the larger the arm's height, the thicker of the layer. And because of the thicker of the layer, the average of the direct constant will be reduced. That means the direct contrast also reduced, and essentially the match impedance between the air and the medium will be reduced. That means the reflectivity will be reduced and the emissivity will be enhanced. So the presence of the rough boundary will substantially change the emission. So in terms of a rough surface, we have to describe it before we can input it to the scaling or emission model. That include the geometry property or geometry structure, either deterministic or random or composite. And another model to describe the rough surface is the dielectric spectrum, either homogeneous or inhomogeneous. So the dielectric spectrum and the geometric structure will be coupled together to make the impedance mismatch between the air and the medium. And also because of the roughness, the mismatch will be reduced. So when we model the scattering or emission, we first involve how to describe the rough surface, include the geometry, structure, and the dielectric spectrum as just mentioned. So to the first order and the second order statistics for the natural surface, which are mostly random. It is about the high probability density and the correlation function, or equivalently the power spectrum density. So, and then we encounter the multi-scale roughness and the long symmetry about the vertical and the horizontal skewness. And also there's a directional dependence on high variations. We call it anisotropy. So we also talking about the median dielectric structure, and include the homogeneous and the inhomogeneous. Here's one example of the soil surface where the dielectric or temperature is non-uniformly distributed, mostly as a function of depth, but it's uniformly horizontally. So here I take one example. The mathematics form of the dielectric profile or temperature profile, as you can make as a function of depth like this, where the beta can change the trend or the rate of the dielectric change as a function of depth. So this kind of a profile will have a substantial impact on the reflection coefficient. Here I take another sample of the dielectric profile. On the first right top panel, we have a coefficient A, and change A will change the rate and the trend of the dielectric profile as a function of the depth. And in the middle, we have a profile 2 and a profile 3, all have a different variation of the dielectric constant as a function of the depth. And at the right panel, we have a profile 4 and 5. So we also plot the reflection coefficient for the case of the flat boundary and the rock boundary. And then you can see even change the coefficient A, and the reflection coefficient will have substantially different. And the interesting point to note is that for the vertical polarization, there is a Bruce angle. It doesn't change even you have a homogeneous or inhomogeneous, or you have changed the rate of the change. But for the profile 2 and the profile 3, and then you can see compared to the homogeneous, they have a substantially change, even the Bruce angle are shift. And more appearance is like that on the right panel. For this kind of a profile, the reflection coefficient will have substantially different. Even the Bruce angle will not, at the Bruce angle there, the reflection coefficient not hitting to 0. So from this example, as the homogeneity change in terms of the dielectric profile as a function of the depth, there's a substantially variation of the reflection coefficient that will have a impact on the final scaling coefficient or emissivity. So here in terms of the biostatistical scattering, we plot in the hemispherical plot between the homogeneous and inhomogeneous. On the top row is for homogeneous, and in the second row is inhomogeneous, and the lower row is the difference between the homogeneous and the inhomogeneous medians. And you can see on the right hemisphere is a backward direction, and on the left hemisphere is a forward direction. And then you can see the most striking impact is on the forward directions. And we have 4 linear polarizations and 2 circular polarizations, and you can see substantial change either for the circular polarization or the linear polarizations. So these examples tell us that the direction profile as a function of depth will have a significant impact on the final scaling strength. So talking about the direction spectrum, and I want just to make some comparison between the 2 popular model. One is the Dobson model, and the other is the Milov model. And then we compare these 2 models with the TDR measurement measured at the EMSL by Pablo Pomoloni's group. The soil surface is essentially a sandy soil with a depth of 2.5 centimeter, with a moisture content of around 14%. So for the real part, you can see the 2 models. One is overestimate compared to the measurement, and the other is underestimate. For the emergent part, essentially is quite close. So let's comparison also tell us that the use of a different direction model also generates as expected quite different of the scattering strength. So the different model which use for the actual permittivity to soil moisture conversion or moisture to soil permittivity conversion will induce a significant bias when you estimate the soil moisture. So another aspect is a spatial dependence on the direction. So that is a spatial anisotropy. So for this example, the ocean wind, the upwind and downwind will have clearly, geometrically speaking, have a different cross-section. Or equivalently, we can say that they will, as expected, the different radar cross-sections. So from the radar observation, you can see the upwind and downwind have a different scaling strength. For upwind, there will be higher. That's well-known features. So in the model simulation, if you didn't account such asymmetry due to the upwind and downwind generate the anisotropy, you will produce quite an error in upwind and downwind ratio. So when the system is covered by oil, and that form as layers. So as a layer, the reflection coefficient will be also changed. And also for this case, when there's an oil cover, the ocean spectrum must be modified because of the damping effect. So without this modification, the scattering and the emission prediction will have a bias or even large error. So here I plot the VB polarization for the scattering in two cases. One is a clean surface, and another is oil cover. So you can see the difference, particularly in the backward directions. So the case here is for oil thickness about 1 millimeter, and the water content under the moderate wind speed 5 meters per second, and incident angle 30 degrees. And also we plot the VB polarized bistatic scattering coefficient response to the oil thickness. You see compared to the clean surface. When the surface thickness increase, the scattering pattern also change. So that tells us the fact that if they have some film form on the surface, the Dulles constant will be changed. The structure of the surface also change in the context of the scattering and the emission. So many surfaces in nature have a multi-scale roughness. Here I want to show you how the multi-scale surface change the scattering coefficient. So we compare one single scale and another multi-scale. With the multi-scale, we linearly combine the Gaussian correlation as the expression here. You can see the CGG means 3 terms of the Gaussian correlation function. On the top is a single scale with exponential correlation function. So essentially, there is 2 correlation function. One is represent a single scale, another represent a multi-scale. And we match the model prediction with the data, measurement data by O. And then you can see 3 frequency band, all the comparisons is quite well. So that means that the model parameter generally is only affected. That represents terrain physical or geometric property, which is responsible for generating the data collected at a specific frequency or a range of frequency. So for an ideal single scale surface, the model parameter in theory must agree with the surface parameter. But for unknown multi-scale surface, the model parameter retrieved from a data set is the only effective parameter. So in terms of the inversion, the single scale or multi-scale will confuse the inversion. So here is another example. Suppose the surface is a multi-scale, and we construct a multi-scale to represent the surface. One is from Gaussian, as I just mentioned, and the other is X power combination. So if we look at the correlation coefficient between these 2 combination of the correlation for the multi-scale, this function appears very close to each other. But there's a difference in backscattering prediction because there's 2 correlation functions represent different surface curvature. That further confuse our inversion. That means that the curvature of the surface actually is a very important consideration in modeling the scattering, especially in the intermediate or high frequency region. So the basically coefficient plot at L band, C band match the data is shown on the right panel. And then you can see even different, even the very close form of the correlation of function will provide different predictions. So one typical multi-scale surface is an ocean surface. And you can see there what we plot the surface correlation function for the different spectrum. We use Appel, Haney, and the Huang spectrum. So for the upwind and the crosswind, the correlation function is quite different. For the upwind direction, there's an oscillatory and with a number of zero closing. For the crosswind, it seems less oscillate and very few of the zero closing. So if we further to plot the correlation coefficient or the correlation function at a different speed, we will see the degree of oscillation will change as the speed change. And also the feature of the oscillation at the crosswind and the upwind at a different speed are even more apparent. So that means for multi-scale surface, the correlation function always have an oscillation with the number of zero closing. That means that the correlation function with the modulation feature will have a capability to represent the multi-scale roughly. So we propose a correlation function with a baseband without modulation. That is a single scale. And the modular with the carrier that can effectively represent the multi-scale. And also by changing the carrier, that's a modulation ratio, we always can produce quite effective feature to represent the multi-scale roughness. So on the right-hand side, I plotted the correlation function for the soil surface, and then we compare the modulated correlation function with the measured correlation function. And then we can see the match between the modulation model function and the measured correlation data is quite well. So essentially, the modulated correlation function are very effective to contain a multi-scale roughness. And in the following, I'll make some example to apply the modulated correlation function to model many natural surface. And for the baseband correlation function, we either can choose the Gaussian base or exponential base. So after briefing the surface model itself, I'm talking about now the rough surface scheduling or the emission. So for microwave scaling from a rough surface, basically is a boundary value problem to solve the stochastic wave equation. That is the total field is the incident field plus the scalar field. So the solution for the rough surface scaling, there's two kinds. One is a full wave by matrix equation. For example, the mass of moment, the FDTD, the IEM, and the MM3D. So probably in full wave solution, the most efficient and accurate so far is MM3D by Chen's group. And for the approximation, there's an iterative approach for example, it's a Kirchhoff approximation or the IEM or IEM-based solution. There's also the amplitude expansion. That's for example, it's SPM, or the phase expansion, such as a phase perturbation model, or the slope expansion, such as a small slope approximation model. So they are commonly used model. So each has their own applicable range. So in this talk, I will use the IEM or AIEM for the illustration as follows. So I'm not going to detail the model development because it involves complex mathematical derivation. It's quite a tedious work. So for the iterative approach, like the IEM, the first step is to formulate a pair of integral equations governing the surface field, which is a sum of the Kirchhoff field and the complementary field. And the Kirchhoff field actually essentially is used as an initial case to start the iteration. So the surface field can be a sum of the Kirchhoff field and the complementary field. Here, L, E1 or L, E2 or H1 is an integral differential operators. So by replacing the Kirchhoff field into the unknown field within the operator, we are able to obtain the surface field estimate. And with the available surface field, then we can compute a far field, scalar field by Stratton-Drew's formula as follows. And then the scaling coefficient are compute. So in estimate the surface field, we are working on a local coordinate, which is to present the n vector and the t vector, and they are close, the d vector. So after a lengthy manipulation of the mathematical direction, the scaling coefficient has two parts. One is single scattering, and the other is multiple scattering. For the single scattering, we also have three terms. One is Kirchhoff term, and the third term is a complementary term, which is a correlative field for the Kirchhoff field, and also have a coupling term. So this is the result of the decomposing the propagation base. And for the multiple scaling term, there's a Kirchhoff cross term, or a coupling term between the Kirchhoff field and the complementary field, and also the complementary field itself. So as a result, the single scattering and multiple scattering has some of the amplitude field. And for the single scattering, it involves one summation. And for multiple scattering, they involve two summation and up. So the total term for the AIEM will be like this. Although they are huge number of the term, but essentially the computation of the scaling coefficient is quite straightforward, and it is very easy to implement in terms of the coding. So for the single scattering, for example, it's quite a symmetry in terms of the coding, and it involves the power spectrum density or the correlation function. And another to account for the asymmetry is the bispectrum density or the bicorrelation function. I'm not going to much detail about this, and there's a paper on the literature you can refer. So for the AIEM model, there's one example of the correlation function for the sea surface. That has been proposed many years ago. So I'm not going to repeat here. So because of the surface roughness and because of the inhomogeneity of the median, we have to modify the reflection coefficient. And we also have to modify the reflection coefficient due to the roughness instead of the boundary. And one effective means to introduce a transition function as a function of the roughness and the sensor parameter, for example, the instant angle or polarizations. And you can check on the literature paper for more detail. So far we are only talking about the scaling coefficient. So how about the emissivity? So we have to first check the energy conservation. That's a reflectivity plus the transmittivity must be equal to 1 in theory. But in practical, particularly for the physical model, some kinds of approximation must be met. So the energy conservation will not be able to be perfect and never be perfect. But the issue is to make the conservation as much better as possible. So once we have a reflectivity and a transmissivity, so if the host space or is a half space, then we are able to compute the emissivity from the reflectivity. So here the emissivity is 1 minus reflectivity, the coherent reflectivity, and the diffuse reflectivity. And the feature is computed from the scaling coefficient in upper hemisphere. So I want to present some of model performance compared to the simulation by MM3D, and also to by matching the data that by own. So we have a 3 polarization, HHVV and HV, both co-pole and cross-pole. So you will see the matching between the simulation and the model predicts quite well. All the regression coefficient about 0.96. And the RMS is within 2 dB, which is quite good. As for the data comparison with real measured data, the regression coefficient a little bit lower, where it's around 0.9, and the RMS is about 2.6 dB, which is acceptable. And all the comparisons are with the 3 frequency band. And now we also have a compare the model prediction with the other model that's like SPM or the dubious empirical model, and the MM3D versus the arms height and permittivity. And you see the matching between this is quite good between the IEM prediction and the MM3D. We also assess the performance of the emissivity predictions, and I believe it's quite good. And we collect quite a huge number of the simulation from MM3D. And you see the regression between the model and the numerical simulation. And for the H polarization and the V polarization. And we apparently can see the H polarization has a better matching compared to the vertical polarizations. And we also have a large number of samples from the small experiments 06 between the model and the data for the emissivity comparisons. So there's a for look angle and two polarizations. And the table on the right-hand side shows the IMSE and the BIOS, and the unbiased IMSE is quite good at the or give the good regression coefficients. So applied to the model to predict the measurement from aquarius for the sea surface L band, and the wind speed dependence and the instant angle depends looks quite good. And how about the comparison between the model and the MM3D for the depolarized backscattering coefficient at L band? And we have three different roughness surface. One small slope and in the median, and the largest slope and or large roughness. And the data matching the model predictions are all comparable. The model we select here is the SS2, second order SSA, and second order SPM, and the AIEM. So overall, the model predictions correlate quite well with the pulsar data. And then you can see that the dielectric constant, when the dielectric constant increase, the measured data is the oscillated behavior. And I believe such a phenomenon is not uncommon in practical measurements. So the numerical MM3D predicts quite well the dielectric behavior, particularly a higher dielectric constant, but gives a smaller dynamic range of the depolarized backscattering compared to the SSA2, SPM2, and AIM. So I also believe the overall the IEM prediction are quite close to the MM3D result compared to SSA2 and SPM2. But all three models give a reasonable well match to the pulsar scale data for all the three samples. So how about the homogeneity effect? How to interpret the variation of the data. The measured data is from Ullrich group, and we can see the homogeneous surface and inhomogeneous surface will give quite a different result in the azimuthal dependence. So when you account for the inhomogeneity into the model, apparently the model prediction match much well with the measured data, and you can much better to catch the azimuthal variation for all three polarizations. I better jumped fast because of the time limit. So for the spatial anisotropic effect, we propose a generalized power law correlation function, or power law, generalized power law PSD like this. And there's quite a number of the degree of freedom to adjust the anisotropic. So we choose several different independent measured data at a different frequency to match to study the spatial anisotropic effect. And with the isotropic, the model are not able to catch the angular trend at the level of the change at the all frequency band we look at here. So the mismatch angular trend and magnitude level simply use the isotropic spectrum. It's no matter which scaling model you are used, or even a numerical, more accurate numerical model like a MMS3D. So it demonstrates the isotropic effect is practically useful to categorize even the bare agricultural soil backscattering. That is especially for the plow soil practice. So the result here to give a hint that if the soil moisture is our primary interest, then we better configure a radar observation geometry to minimize the spatial anisotropic influence. Because the anisotropic influence here we show is so strong. So here's the power density function. We look at the instant angle at a 38 degree with the wind speed 10 meter per second. And L band, C band, X band, and the K band, both the HH and the VV polarization. Even with the same scaling model, if the input to the model with a different spectrum, then you generate quite a large variation of the backscattering coefficients as a function of wind directions. Here we choose a form spectrum, Duran and Versesky, and Appel, Urahani, and Huang spectrum compared to the measured data from Aquarius satellites. And we also compare with the geophysical model like C-band, X-band, and Ku-band and SCAT4 models. So all reveal the different spectrum model input to the scaling model will generate a huge difference of the backscattering coefficient. So the anisotropic effect also must be included. Like here, even we use the Appel spectrum for the model simulation to generate the backscattering coefficient. The dashed line is not accounted for the asymmetry, and the solid line accounted for the asymmetry. Then you can see the model prediction will match much well with the data. So the multi-scale roughness with the modulated correlation functions also applied to the soil surface. All the matching between the measurement at a different frequency band for soil surface and the snow covered sea surface are all tell the truth that the multi-scale roughness really is there and must be included in the model predictions. And for the snow surface, the emissivity or the brightness temperature also influenced by the multi-scale roughness. So without accounting for the multi-scale, we are not able to measure the data all the way from small look angle to large look angle for both vertical and horizontal polarization. So because of the time limit, I'm not going to much detail about the application of the MCF to consider or to account for the multi-scale roughly in the ocean surface. And finally, I will show the application of the modulated correlation function to account for the boundary effect in the snow-covered sea ice hosted by the ocean surface. So the comparison of the emissivity between the measured data and the model predictions from cold, warm, wet, snow-covered first year sea ice at the 3 frequency band at both H and the polarization. So for the polarization difference and for the frequency difference and for the ice type difference, you can see it's quite accountable to apply the modulated correlation function to account for the multiple scale roughness of the boundary between the snow, sea ice, and the ocean. So we are also able to look at the range of the brightness temperature as a function of look angle for snow cover ice. The brightness temperature range is about 6 to 75 K for dry snow cover ice and about 7 to 12 K for the wet snow cover ice. While for the bare surface, pure surface without snow cover, the range is about 35 to 45 K. So we also compute the maxima and the minima brightness temperature as a function of a look angle for both H and the V polarization at the C band. And the parameter for 7 types of the snow cover ice is listed in the table on the left-hand side. So in comparison, we can see the dry snow cover multi-year or the first year ice will generate much higher brightness temperature variations compared to the wet snow cover, either multi-year or first year. So pure ice, multi-year or first year without snow cover have an immediate range of the temperature variations. So after many illustrations, I want to make some remark. The model parameter are generally effective parameter that is representing the terrain physical or geometric property, which are responsible for generating the data collected at a specific frequency or a range of frequencies. So I want to emphasize once more that for an idealized single-scale statistical surface, model parameter always must agree with the surface parameter. But for unknown multi-scale surface, model parameter retrieved from a data set are only effective parameters. So data interpretation exercise must careful to require that the selection of an applicable model include both surface and scaling emission model. So in most of the cases, the failure in the modeling is not due to the model itself, but due to an incorrect assumption about what should be a model. So when there is a surface cover, like a snow cover sea ice, or the oil cover sea surface, a volume scattering layer appears. So in basically, the volume scattering tends to dominate mostly at a large angle of incidence. So I want, in my humble opinion, the future work include how to assess the difference between the model prediction and measurements, because we are involved so many uncertain surface parameter in layer median or in a raw boundary, such as the snow cover sea ice, vegetation cover ground. So the variability of the scattering emission due to the surface parameter error and the bias must be assessed. And also, I feel that the more accurate direct model for various raw boundaries are required. For example, the C form. Because the C form, it will change the direct property of the surface, depending on the water fraction, thickness, and bubble radius. All this change the scattering emission behavior. Lastly, I want to point out that exploring the AI or machine learning to enhance the scattering emission model using the data-driven approach, maybe it's the next task to pursue. So that basically conclude my talk. Finally, I want to acknowledge that this talk is dedicated to Professor Adrian Fong, who told me the rough surface scattering and guided me to work in this exciting field of research. And a constant discussion and inspiration from Professor Nanjing of U Michigan has been wonderful and fruitful. So all the material I cite here is given in necessary reference. So anyone interested can refer to necessary reference book. Thank you for your attention.
Kun-Shan, there are some questions in the chat and the Q&A if you'd like to answer those. I can help if you cannot read them directly.
Oh, there are quite a bunch of.
Would you like them for me to read them for you?
Can you please?
Yep.
Sorry.
So one of the first, so we have a few minutes to answer some questions. We might not get to all of them. The first question we have here is why there's sudden increase in reflection coefficient after 60 degree. You are welcome to also, you can take your presentation down if you'd like, if it's easier to see some of the Zoom.
Yeah, I think so.
Or stop sharing.
Yeah. Okay. Yeah. So can you repeat the question?
Yes. Why is there a sudden increase in reflection coefficient after 60 degree?
Oh, that's I think that's it hits the boost angle. So for the vertical variation, there's a boost angle, right? Depends on the direct constant.
Yes, it is. Yes, it is.
Yeah.
Okay, then there is another question asking how to retrieve soil moisture, but sorry, but I would skip this question because, okay, I take the action to give and to find to a webinar which is specifically on soil moisture retrieval. So in this case, we are speaking about a forward model.
Yeah, I'm just talking about some when you apply the forward model to retrieve the surface, there's many uncertainty. So how to make proper use of the selected model is essential that the care must be exercised to model correctly the surface under sensing. For example, the rough surface or the bare surface or vegetated cover surface.
Probably someone wanted to understand better what do you mean when you speak about spatial anisotropy of the surfaces, and which should be let's say the approach to understand whether an exponential or a multi-scale surface description should be considered.
Yeah, I think that's a question. Good question. And the spatial anisotropy can be generated like in agricultural field is a practice, or the wind blowing the sea surface that generated the asymmetry. For example, the upwind, in the upwind direction, there's geometrically there's a more cross section, right? Compared to the downwind direction, and even compared to the crosswind directions. So that generated the anisotropy. And that's particularly important for the star observation because for the side looking star, depends on the orientation you look at the relative to the field or the surface that you look at.
Okay, one more question was asking whether when you compared the advanced integral equation model and the numerical 3D model, you were considering multi-scale roughness or any anisotropy or just a standard isotropic surface. And he also asked if there is available a version of the IEM considering multi-scale roughness.
Well, yeah, there are two separate issues. One is the surface spectrum input to the AIEM or the SSA or whatever other applicable models. So you have to model the surface itself before you input to the scaling or emission models. And that is nothing to do with the electromagnetic model. So the scaling or emission model only accept the surface you want to look at or you want to simulate. So either single scale or multiple scale of the roughness. So the model itself computation is nothing different.
Another question asking whether there is an open source version of the IEM or advanced IEM.
Well, actually, when I listed the reference, the third reference that we have already provided MATLAB code online. You can access that from the CRC Press, the website. So originally the code was coding in Fortran and Mathematica. Now I think 2 years ago we make the MATLAB version to the public online accessible from the CIC on site.
Okay, Sylvia was asking if the presentation can be shared. So, Kun-Shan, you can send to me the presentation in PDF, and I will share the presentation with any people asking for it.
Sure. I'm more than happy to do that.
Okay, I don't know if there are other questions. There are many, so it's difficult. Someone asked which kind of data have you presented in your comparison when you showed the L band, C band, X band. I think he's referring to the measured data.
Our collected from the literature.
So yes, there are many papers with experimental presenting the result of experimental campaign.
Yes.
And there is also a book, I recall, a very old one, but collecting data and also empirical model fitting of data collected in the past from INUSA. Okay, so
Mauro, this is Nando. Can I ask a question? Because I'm not able to do right. Hi, Kun-Shan, this is Nando from Italy.
Oh.
I would like to ask you a question.
Yes.
Yeah, I would like to ask you a question about, this multi-scale. If I understood correctly, basically the idea is that you decompose the surface characteristic function according to its moment. So you have, zero order tone moment, the first order, which is the spectrum, the second order, which is the skewness, the third one, which is the pickedness. Is it correct?
Yes.
Okay. And then the question is, this kind of higher order moments, of course, affect the correlation function, for instance, and also the spectrum, as you've shown. Is there any chance to relate this kind of parameters to the actual surface parameter? For instance, if I'm dealing with the ocean remote sensing, is there any way to relate the skewness or the pickedness to surface parameter, ocean surface parameters?
Yes.
Good.
Yeah,
okay.
we actually extended word to relate the model parameter related to the physical parameter ocean. For example, the wind speed and the slope and the wave height. And also we borrow the experience from the Cox and Monk about their slope dependence, slope variance.
So the Cox and Monk's PDF.
Yeah, right.
It relates, the standard deviation in the two direction with the wind speed.
Yes.
Okay.
Exactly.
Yes. Okay.
Yes.
Okay. Thank you very much.
Kun-Shan, there is also a question asking whether, in your opinion, the advanced integrated equation model can be exploited to help detecting ships over ocean from radar data. I mean, do you are aware of any work using this model for ship detection purposes?
I don't think so. Because for the model we average infinite sample of the data, and they only can contain many scale, and for the ship detection, for example, from the start, you have to consider the speckle effect, right? So for the model itself, it averages out so many sample of the scattered field. So it's no longer working on it's no longer present the scattered field, but instead in the ship detection or other target detection over the ocean, you have to make it as a coherent. The speckle will contaminate the target detection.
Okay, in any case, this guy was asking whether the model could be in some way included in a machine learning framework to help in this application.
Yeah, I think that's a good try. So that's to enhance the model performance. But as long as you have a good set of the good quality of the data to drive the machine learning.
Yes, that's one of the main points of machine learning approach. I have also a question. You showed the effect of non-homogeneity of the dielectric constant as a function of the depth below the surface, and you showed the magnitude of the reflection coefficient. What about the phase? Because there are some evidence that in SAR interferometry, you can see some phase difference due to change in soil moisture. And there is a model trying to explain this, considering the penetration through the soil and the different penetration depth as a function of soil moisture. But have you also any computation of the phase of the reflection coefficient for different profiles, vertical profiles of the dielectric constant?
I didn't. I only showed in the context of the retrieval of the soil moisture. I think the question is quite excited about apply the interferometry to retrieve the soil moisture, but you have to consider the incoherence or the loss of the coherence due to the moisture change, right?
Yes, but there is an evidence that something happened in the radar interferometry when the soil moisture change. But so it would be interesting to consider the phase of the dielectric of the reflection coefficient for different soil moisture profiles. Yes, just
yeah, I believe so. I believe so, particularly for the inside for the soil moisture. Lower frequency like a L band or a P band.
Yes, of course. Yeah.
It penetrates deeper, and so the dielectric profile as a function of depth must be considered. So where the phase variation must be interesting to look at. Right. Actually, we have a shallow study of the phase variation that also changed because of the presence of a rough surface, the rough boundary on top. So I don't know if, yeah, so it would be interesting to study the sensitivity to the rough boundary or the dielectric profile in the context of interferometry SAR.
Yes, yes. This is a suggestion for cooperation, for instance.
Yeah. Very good, very good. Yeah.
Yeah. Okay, so if there are not more questions from the audience, we have spent more than 1 hour. Yes, more than 1 hour, an hour and a quarter. And I think we cannot ask more to Professor Kun-Shan. And I thank you very much, Professor Kun-Shan, again, and hope to have another other opportunity to have a cooperation in the future together with anyone interested in this audience. So thank you again. Thank you to all the attendees of this webinar, and see you soon for a next webinar, possibly about soil moisture. Why not? Since there was a request from some of the people attending this meeting. So bye everyone. Thank you again, Kun-Shan.
Thank you. Yeah, good night. Bye.